Okay, welcome everyone. First lecture after lunch. You're very welcome to fall asleep, but please don't snore. So yesterday we managed to prove Jacobi's triple product identity, and I promised you some applications before we proceed with Rajers-Ramanujan, the proof of Rajers-Ramanujan identities. So let's remember the JTP. It said a bilateral series n running from minus infinity to plus infinity, minus 1 to n, q to n squared, z to n. This is not an analytic function, but it's a meromorphic function in z, and it equals a triple product, as the name suggests, in which we have the arguments z times q, q divided by z, q squared, semicolon q squared sub infinity. So this is the triple product, and it's a highly structured triple product. The product of two of the parameters must equal the second one, the third one, and the third one must be equal to the base. That's the indicator of Jacobi's triple product identity, and you can use it both ways. We saw one corollary known as Euler's pentagonal number theorem. And it said, again, a bilateral sum, n running from minus infinity to plus infinity, minus 1 to n, q to n times 3n minus 1 divided by 2 equals reciprocal of the partition function. So let's see an application of this reciprocal of the partition function. The reason I say reciprocal, because when you multiply them, you get 1, right? So 1 over q sub infinity times q sub infinity is 1. There is more to this. Regard the one on the right-hand side as 1 plus 0 times q plus 0 times q squared, 0 times q cubed. All honest powers of q have coefficient 1 in front of them. The first one is the generating function for number of partitions, which is n running from 0 to infinity, p of n, q to n. Let's write it in brackets. And the second one, thanks to Euler's pentagonal number theorem, is that bilateral series. Let me use a different parameter here, m running from minus infinity to plus infinity. That expression, q to a quadratic exponent, and oh, m, sorry, yes, thank you. This equals 1 plus 0 times q plus 0 times q squared, and so on. Which means that if we multiply out these two series and extract the coefficient of q squared, q cubed, q to the fourth, we can identify those coefficients with the coefficients on the right. Because this is not meromorphic anymore, it's an analytic function in q. So let's write the first few terms here. We have p of 0 plus p of 1 times q, as if we don't know these numbers. p2 of q squared, p3 of q cubed. And then also we need a few terms from the second series as well. Let's write it down. So for different m's, let's calculate these numbers. What is m times 3m minus 1 divided by 2? Well, okay, let's go step by step. 3m minus 1, let's calculate this first. And m times 3m minus 1 divided by 2. Because it's bilateral, we have to consider positive as well as negative values of m. When m is 0, 3m minus 1 is going to be minus 1, and their product is going to be 0. Okay? When m is plus 1, 3m minus 1 is 2. Their product divided by 2 is going to be 1. When m is 2, this is 5. 2 times 5 divided by 2 is 5. If we go the opposite direction, when m is minus 1, 3m minus 1 is going to be minus 4. Their product is positive. And divided by 2, it's going to be, what is it? Plus 2. When m is minus 2, 3m minus 1 is minus 7. Their product divided by 2 is going to be plus 7, extending in both directions. And these are going to be accompanied by minus 1 to m. So let's write it here. Minus 1 to m q to this quadratic exponent. It's going to be 1 here, minus q squared, plus q to 5th, plus q to 7th, minus plus in the positive direction, again, minus plus in the negative direction. Combining together and writing the first few terms, they are going to be 1 minus q squared, plus q to 5th, plus q to 7th. And this pattern will continue forever. The coefficients are going to be plus or minus 1 if they appear. Other coefficients are 0. And the pattern of signs, minus, minus, plus, plus, minus, minus, plus, plus, will go perpetually. Very good. Any questions up to here? And the reason we call them pentagonal numbers is because if you think about square numbers, 1, 4, 9, 16, 25, you can arrange 16 dots into a square. You can make them look like a square, or you can think about triangular numbers, 1, 3, 6, 10, 15, 21. You can arrange them to look like an equilateral triangle. Likewise, you can arrange these number of dots into looking like a pentagon. That's why we call it pentagonal number theorem. Anyway, when we multiply and find the first few terms of that product, the constant term may only come from P0, right? What's going to be the coefficient of Q? Well, we can multiply this one with the linear term here, or the linear term in the second brackets with the constant term in the first. So this is times q to 0 plus p1 minus p0 times q to 1 plus what's going to be the coefficient of q squared? Well, multiply these two things, those two things, or these two guys. So it's going to be p of, no, minus p of 0. Yes? Let's start with p of 2. P of 2 minus p of 1 minus p of 0, q squared, and you can keep doing this. This is going to be identified with 1. That is going to be identified with 0. This is going to be identified with 0. If you do things in the right order, you'll see that p of 0 equals 1, which is otherwise known as the empty partition of 0. Plug it in the second equation, p of 1 is going to be 1. Use these two pieces of information in the third coefficient of the quadratic term, p of 2 is going to be 2. Using these three pieces of information, use the coefficient of q cubed, you get p3, and then you get p4, you get p5, p6, and so on. So remember, Walter mentioned McMahon found p of 200, and he challenged Hardy and Ramanujan to do the same. This is McMahon's method. So he found everything, all partition numbers up to 200. There's more to this story, but I'll tell you the story after we prove two more corollaries. Any questions here? So this is one way to find partition numbers, an elementary way to find partition numbers, and you can do it by hand. You can manage things up to 30 or even 50. With the help of a computer, you can go up to, for larger numbers, 200, maybe 500, maybe even 1,000. This is feasible. For those of you who cares, this algorithm to find partition numbers has polynomial complexity. Okay, so here's JTP, here's Euler's pentagonal number theorem. Let's write another convenient form of JTP. I'll just tell you the substitutions. You can follow them easily. First, replace Z by Z divided by Q. Then replace Q squared by Q. And then you get another form of JTP, which is from n minus infinity to plus infinity, minus 1 to n, q to n choose to z to n equals z, q divided by z, q semicolon, q sub infinity. This is one form of JTP. Now notice that in this form, if you plug in z equals 1, the right-hand side is going to vanish. Let's call this star. Sorry about that. In star, if we plug in z equals 0, what did I say? If we plug in z equals 1, I'm sorry, makes the right-hand side 0. Therefore, it must make the left-hand side 0 as well. I hope it doesn't happen again. Anyway, we can separate that factor and we can rewrite star as the following. We can write that bilateral series divided by 1 minus c. Remember, 1 minus c is the first factor in the first batch of infinite factors there. If we take it out, the next factor is going to be 1 minus z times q. If we start there, the remaining is going to be zq, q divided by z, q sub infinity. We can plug in z equals 1 here and get something non-zero. And what do we get? We have q sub infinity raised to q. But on the left, we cannot immediately set z equals 1, but this is a meromorphic function, and by the look of it, at z equals 1, we have a removable pole, a removable singularity. So z equals 1 must be a removable singularity. In other words, we can calculate the limit as z approaches 1. Because it makes the denominator 0, it makes the numerator 0 as well. We made that observation a minute ago. We can apply L'Hopital's rule. And don't worry about convergence because Q has a quadratic exponent here. No matter what Z is, it will beat Z in the long run as long as Q is less than 1 in modulus. That's going to converge absolutely. Once again, L'Hopital's rule applies. And don't take this for analysis. We are still in the realm of calculus. Okay, take the derivative, take the Z derivative of the top, take the Z derivative of the bottom, and then plug in Z equals 1. Once you clear the denominator, plug in Z equals 1. We are going to get, because of absolute convergence, we can differentiate term by term, minus 1 to n times q to n choose 2 times n. Yes? It must be so. Yes, because derivative of z to n is n times z to n minus 1. And don't worry about negative exponents because we are plugging z equals 1, not z equals 0. Divided by minus 1. We can write this series in a better way. Again, we got to calculate these numbers n choose 2 for positive n as well as negative n. So when n is 0, what's n minus 1? And what's the binomial coefficient? N choose 2. And then, of course, we have the term minus 1 to n, q to n choose 2. Let's see what that is. So this is going to be minus 1. The binomial coefficient is 0. No, I forgot the minus sign at the bottom. So the term corresponding to this will be minus 1. Okay? When n is plus 1, n minus 1 is 0. So n choose 2 is going to be 0. Product divided by 2. This is going to give us plus 1. What did I forget? I think we forgot n times. Yes, thank you. Well, I wanted a red one. So we have n here. Oh, so I lied. So this is 0 times 1. This is 1 times q to 0. Okay, very good. When n equals 2, n minus 1 is 1. This is going to be 1. Q to 1 times 2. 2 times q to 1. Yes? Minus. No?
Yeah, it's negative.
Is it negative? N equals 2. Oh yes, that's negative. Thank you. And if we go the other way, when we plug in n equals minus 1, this is going to be minus 2. The binomial coefficient is 1. Minus 1, another minus 1. That is plus 1 times q. Yes. Yes. Looks correct up to here. Minus, plus, plus. Anyway, 3, 2. Let's do it for n equals 3. I want to find a pattern and I want to merge the two directions of the series, make it a unilateral series. That's my goal. The binomial coefficient is 3, minus 1 raised to 3, another minus sign, that's going to be plus 3 times q squared. The other direction, q cubed. Oh, thank you. Minus 2, minus 3, plus 3 here. It's going to be q cubed minus q cubed, minus 2 times q cubed. 3 minus 1. Am I doing something wrong?
Why do you calculate n minus 1?
Because it looks like we have 1 minus q plus q cubed minus the next thing. Are we missing something? Okay, let's go one more step. When n equals 4, this is 3, the binomial coefficient is going to be 6. Minus 1 to 4 with an extra minus sign, 4 times q to 6th. Minus 4, 6 here again, plus 3 times q to 6th. I think this pattern continues. Am I missing something? We shouldn't be. Collecting all we have, these are the constant numbers. These are the linear terms. No quadratic term. These are the cubic terms. These are the next ones. And the coefficients appear to be plus 1, minus 1, plus 1, minus 1. And we have the triangular numbers in the exponents. I feel that I'm making a huge mistake here. But we follow the operations correctly. We plugged in z equals 1. We took the derivative as instructed. We must be on the right track. I was hoping for something else, to be honest. So it looks like unless I'm making a huge mistake, it looks like we have q sub infinity cube equals from n equals 0 to infinity minus 1 to n q to n choose 2. I will double check this and get back to you. Anyway, here's the thing. Back to the story. So McMahon found the table of partition numbers up to 200, and he gave it to Hardy and Ramanujan. Ramanujan looked at it, and he noticed that P of 4, P of 9, P of 14, P of 19, P of 24, basically, beginning with the fourth one, every fifth partition number is divisible by 5. But any one of us could have noticed that because numbers divisible by 5 end in 0 or 5. But then Ramanujan went further. All are congruent to 0 modulo 5. This is Ramanujan's observation. The second one, he also noticed that P of 5, P of 12, P of 19, P of 26, you get the picture. Beginning with the fifth one, every seventh one of these partition numbers are divisible by 7. And also, he noticed that P of 6, P of 17, P of 28, P of 39. You get the idea. Beginning with the 6th one, every 11th coefficient is divisible by 11. They are later proven, and they are called Ramanujan's congruences for the partition function. I don't want to go too deep into congruence stuff because I don't do research on them myself. Also, we have another goal, but why did I give you those corollaries? The pentagonal number theorem and the second corollary we derived, which I have some doubts on. I mean, if you do calculations correctly, you will get an identity like this. I just need to check the coefficients here. But those two, pentagonal number theorem and this one, will help you prove the first two congruences. Let's write it down. The pentagonal number theorem and let's call it double star. If I wrote it down correctly, prove the first two congruences. Any issues, any questions? How do they exactly prove this? Once again, it's elementary number theory, and as we've been doing college algebra, you can find at least two different proofs for these, one of them based on these corollaries, these formulas and corollaries in Burn's book. Easy proofs are in number theory in the spirit of Ramanujan. Çok yaşa. So look at that, and if you happen to have any questions, just send me an email or find me here. Let me tell you the end of the movie. Let me tell you the end of the proof for Rogers-Ramanujan identity so we don't lose time for that. The conclusion of the proof will go as follows. Proof of Rogers-Ramanujan identities, both of them, will be the following. We will have, after many computations, and running from minus infinity to plus infinity, minus 1 to n, q to 5 times n choose 2 times q to minus 2n, divided by QQ infinity, or this series multiplied by the partition function. And using Jacobi's triple product identity, we will convert this because q to 5 will play the role of q, q to minus 2 will play the role of z there. And for some reason, I didn't like this. I want this to be plus 2 here. Yes. This is going to give us q squared, q cubed, q to 5th, sub infinity. And if you dissect this into 5 pieces, take the factors where q's exponent is 1 modulo 5, 2 modulo 5, 3, 4, 5 modulo 5, you will have the dissection, 5 dissection, q squared, q cubed, q to 4th, q to 5th, q to 5th, sub infinity, lots of cancellations, q squared, q to 5th will go away, q cubed, q to 5th will go away, and these last factors will go away. You are left, as Johan told you yesterday, 1 over q, q to 4th, q to 5th, sub infinity. That will be the conclusion of the proof. I'll tell you the beginning later. And for the second Rogers-Ramanujan identity, everything will be the same except this plus 2n here will be plus 1 times n. And that will give you the product q, q to 4th, q to 5th, q to 5th sub infinity divided by q sub infinity. And after similar cancellations, you're going to end up with q squared, q cubed, q to 5th sub infinity. The first line is for the first Rogers-Ramanujan theorem, second line for the second one. So partitions, we will end up with partitions which are 1 or 4 modulo 5. And in the second one, we end up with partitions into parts that are 2 and 3 modulo 5. So that's going to be the end of the story. Questions? Yes?
Can you keep the signs on the negative side of that calculation?
On this board? So let's see. -1 to -1. -1 raised to -1 is -1 with an extra minus sign. That's going to be plus.
Then you multiply the -1 because n is -1.
Oh, n is -1. Oh, we have extra minus signs as well. Okay. So this is going to be minus q, yes? This is going to be plus 2 q cubed. This is going to be minus 3 q to 6th. That's what I was looking for. Thank you, thank you. Yeah, n is negative to start with. That's what we missed here. And then, yeah, as we suspected, it's going to be 1 minus 3 times q plus 5 times q cubed minus 7 times q to 6th. Very good. Thanks a lot. Thanks a lot. So, okay, you will have a 2 times n plus 1 here. Yes. That relieves me a lot. What is it?
Where the last -1 comes from?
The extra minus sign we forgot is this one.
Oh.
Okay. That's with that extra, everything on the left will reverse sign, and then we'll be able to combine those coefficients. And we will have 2n plus 1 here. Yeah, I remember it was 2n plus 1, but I messed up the computations. Thanks a lot. Okay, any other corrections? Now, let's consider the two classes of partitions where the conditions are given by Rogers-Ramanujan identities. Here's the start of the proof. Let me write the identities in Schur's notation. Because he proved these independently using entirely different ideas. So number of for any n. Number of partitions of n into distinct and non-consecutive parts so nothing is repeated, no part is repeated, and no part comes too close, equals the number of partitions of n into parts that are 1 or 4 modulo 5 or plus minus 1 modulo 5. That's the first Rogers-Ramanujan identity. The second one, number of partitions of n into distinct and non-consecutive parts, all of which are greater than or equal to 2. So no one's in the second Rogers-Ramanujan identity, equals number of partitions into parts that are congruent to plus or minus 2 modulo 5. So no one's. We will call the first enumerand R sub 1 of n. Call this number R sub 1 of n, and call the second number R sub 2 of n, for obvious reasons. Is this enough? Unfortunately not. We have to count such partitions, and we have to count the number of parts as well, so we can get recurrences. Let me leave the final part here. We will refine and we will set R1 of m and n, number of partitions counted by R1 of n, which have exactly m parts of n counted by R1 of n having exactly m parts. Okay. R2 of m and n likewise. R2 of n, number of partitions counted by R2 of n with exactly m parts. And we will play the following game. Claim 1. R sub 1 of m and n minus R sub 2 of m and n they have almost the same conditions, except that the first one allows ones, the second one doesn't. So the difference, in the difference, we will have exactly one part that equals 1. Same conditions, but in the first one, parts are greater than or equal to 1. In the second one, parts are greater than or equal to 2. This must equal something. How do we count what it equals? Well, The difference is, again, Rogers-Ramanujan partitions with exactly one part that equals 1. So we will have 1 that's fixed there. The next part cannot be 2 because parts cannot be consecutive. They cannot come too close to each other. All parts are greater than or equal to 3 here. But they are still subject to Rogers-Ramanujan conditions. We didn't define any R sub 3. We don't want to define R sub 3, so we are going to do the following. If we take this partition and subtract 1 from everything, subtract 1 from each part, this one is going to be killed, yes? It's gonna be 0, and we can put it aside. And the rest of the parts will be greater than or equal to 2, therefore they are going to be counted by R sub 2. 1 disappears. Rest is greater than or equal to 2. Because the original parts were satisfying Rogers-Ramanujan conditions, if we shift them by 1 unit to the left, they are still going to satisfy Rogers-Ramanujan condition. They are going to be distinct and non-consecutive. Nothing was repeated to start with. Nothing is repeated after the shift. Nothing was too close. No two pairs were too close to each other. They cannot be too close to each other after the shift because everything is shifted by 1. So this is going to be counted by R sub 2. However, the number of parts dropped because we killed 1 part. So number of parts becomes m minus 1. What about the weight of the partition? Which number are we partitioning now? Well, there were exactly m parts. We subtracted 1 from each of them, so we lost m in the weight. So please look at this and tell me if you have any questions. This is the first claim and its proof. And I think it's the first time I showed you a combinatorial proof, yes? Yeah. All right, that's the first claim. The second claim is going to be shorter. And the proof is going to be shorter too. Claim 2, R2 of m and n is going to be R1 of m and m minus n. How do we see this? If we have a Rogers-Ramanujan partition where everything is greater than or equal to 2, shifted by 1, shift every part 1 unit to the left, now parts are greater than or equal to 1, they still satisfy Rogers-Ramanujan condition n minus m. We don't want negative weight, sorry. Because we shifted each part by 1, minus 1 times m, that's how much weight the partition lost. That's the second claim. Of course, if m is equal to n, you cannot have any such partitions. For instance, if you want R1 of n and n, this is going to be 1 if n is equal to 1, because 1 by itself is a partition of 1, and it vacuously satisfies Rogers-Ramanujan condition. But otherwise, if you have 5, and if you want to write a partition of 5 into 5 parts, still satisfying Rogers-Ramanujan condition, you won't be able to do that. So you have such boundary values. You can get the boundary values just by looking at the combinatorial description of the enumerants, combinatorial description of the partitions. Now, Joanne told us in the morning how to pass from recurrences between enumerants into functional equations between generating functions. We will do the same here if we set R1 of x. Q will always be there, so I'm not gonna write it. M and n greater than or equal to 0, R1 of m and n, x to m, q to n, and R2 of x. Similarly, the enumerant is R2 of m and n now. Then we can translate these claims into functional equations between these generating functions. That's what we're going to do next. In order to do that, we'll take the claims, claim 1 and claim 2. Claim 1 is not exactly visible. Let's see it. We will take claim 1 and claim 2, multiply both sides by x to m, q to n, and take the sum over non-negative m's and n's. I don't like the silence. Please ask me some questions. How many of you are with me so far? Okay. If we have to go back, where do we go? All right, let me just continue then, because we will do things in other flavors as well. We will be getting power series expansions. We'll be writing power series for these generating functions in a minute. And we'll talk about unique determination too. So, as I said, let's multiply both sides of claim 1 by x to m, q to n, and take the sum, take the double sum over non-negative m and n. And something interesting will go on for the second sum, m and n greater than or equal to 0, R2 of m minus 1, n minus m, x to m, q to n. First of all, number of parts cannot be negative, so we can exclude m equals 0. So we can write m is greater than or equal to 1 here, n can still be greater than or equal to 0. No, n has to be greater than or equal to m. Okay, so let's take care of the second index first. Replace n by n minus m. No, n plus m. When you do that, this will become just n, yes? But the exponent of q will become, what is it? Q to n plus m. That's the first thing. The next thing we want to do is replace m by m plus 1. Do we have a yellow chalk? Yes, we do. Replace m by n plus 1. And of course, after the first substitution, after the first shift of index, n is going to be greater than or equal to 0. After the second shift, m is going to be greater than or equal to 1. This one becomes m. This is still n. This is going to be x to m plus 1. And this is going to be q to n plus m plus 1. I didn't want to do that, but I have to erase this and keep working with this equation. On the left-hand side, we don't need to do anything because it's just going to be a difference of two generating functions. So on the left, we are going to have r1 of x minus r2 of x. On the right, what do we have? Well, let's write it out here first. M and n, both greater than or equal to 0. R2 of m and n now. The exponent of x is x to m plus 1. Let's take one of them in front. In fact, let's take the q in front as well. We have a dangling q there. And let's couple q to m with x. So we have x times q raised to m, q to n. Once we do this, we will see that this is r2 of x times q. Before, yeah, we forgot x times q. Yes, thank you. X times q times r2 of xq. The second claim is easier. Very similarly, this time you just need to replace n by n plus m, and that will have the effect of multiplying x by q. You will have r2 of x equals r1 of x times q. So, Jean, how did you classify these equations? Degree, what did you say? Order, degree? Order, okay. So these are pairs of equations, a system of equations defining Rogers-Ramanujan generating functions, and the system has order 1. An order 1 system of q difference equations defining Rogers-Ramanujan generating functions. If you try to eliminate either one, if you want to get an equation purely for R2 or purely for R1, you have to sacrifice something. The order will be 2. If we want to eliminate one of the functions here, we will have one equation, yes, only one defining equation, but the order is going to be higher. But I'm not going to show you this explicitly. If you want, you can do your own computations. Okay, this is another place where we will change gears. Any questions? Okay, now we define these guys as double sums, yes? Double sums over m and n. Believe me, these are analytic functions inside the unit disk, so the radius of convergence is 1. Maybe we have a larger radius of convergence, but anyway, they are analytic inside the unit disk. Therefore, we can write power series in terms of x. Am I going over time? Am I? Oh, really? Okay, then the checkpoint, let this checkpoint be the end. We will take it from here next time. Thank you for your attention.